Okay, hello, good morning, afternoon, evening to everyone. First question is the usual one. Can you hear me? Can someone type in the chat? Can you see us? You're supposed to see 3 screens. Someone can use the chat to say, can you see 3 sub-screens? Okay, terrific. So thanks, Daniel, Alec. Okay, good. Okay, great. So very happy to start another Stark at Home episode. I think it's something like number 15 or something like that. And this time we have a very special and honored guest who's going to be speaking most of the time. This is a Professor Madhu Sudan of Harvard University. I'm not going to go over all of his amazing biography, just a few highlights. He won the ACM Best Dissertation Award for his PhD back in the day. He won the Nevanlina Medal for his works on things that he's going to talk about today. He's a member of the National Academy of Sciences. He won the Gödel Prize and a bunch of other things. So Madhu, among his many achievements, is a very major contribution and co-invention of the PCP theorem, that is really the theory that is behind a lot of the succinct interactive proof systems, and in particular Starks, which we use at Starkware. He's also a scientific advisor to Starkware. And without further ado, I'm going to hand it over to him. I just want to remind you that there's the Ask a Question button. So here's like a test question. And from time to time, we're going to go and review that thing. It's better to use that, the Ask the Question, rather than the chat, which we won't be following. So Madhu, the floor is yours, and I'm going to close my screen and become smaller. Okay. Please.
Okay, great. Thanks very much, Ellie, for inviting me here. Thanks to all of you for showing up. I was hoping that I could see all the questions fly by on chat, but if that's not going to happen, Ellie, please do interrupt me anytime you see an interesting question. I would be very happy to make this as interactive as possible. For those of you who are listening in, I should say that as I see the chat, there seems to be some delay between a question that Ellie asked and the responses that we got. So if your responses are being addressed to in some delayed fashion, please don't worry about it. Your question probably does get registered. Okay. All right, great. So what I'm going to talk about today is sort of a story that weaves through information and communication and computation. And it motivated me to start thinking about, the revolution that we live in, the fact that we can take any piece of any aspect of our life and convert it to a certain number of bytes, whether it's, up to recently, we've been able to, it would have been very surprising about 30 years ago to say everything, including music, video, all your files, everything is just measured in bytes. Now we are in that stage. And if the theory of, consciousness and so on are successful, maybe in a few years from now, we'll be measuring pain in the number of bytes of pain that something is causing, or happiness in the same way. So amazing successes in information theory. So I want to talk a little bit about this communication and computation, the origins, how did we get here? That's the kind of a question that I want to ask, and try to give you some sense of what I feel about that. That'll lead us into the theme of error correcting codes. One of the original questions that came in the intersection of communication and computation was, how do you keep data in a reliable fashion? And that'll take us to the topic of error correcting codes. And then I will expose you to some math. There will be some math in the talk, and I'll keep weaving in and out of the math and the bigger picture. And if you are not very familiar with some of the details that go behind the math, it's okay. You can just sort of zone out for a bit and then zone back in. Hopefully, you'll still be able to get some additional things. So just because you don't follow the current slide doesn't mean you won't follow the future slides. Okay. The third part of this, and I'll get to this when I get to this, is probabilistically checkable proofs. And So these are the three major breakpoints in the talk, and definitely at those points I'll stop for questions. We'll also try to get questions at earlier stages if possible. Okay, everyone with me? I should have checked. We can hear me and see me, right?
Yeah, looks great.
Okay, great, thanks. All right, so the theory of computing, of course, we all know, probably started in the 1930s due to the seminal work of Turing. Turing invented what was called the Turing Machine, a finite state machine which looked at an infinitely long tape. And one of the remarkable things that Turing did was to say that there is this thing called a universal machine. This is a particular code that you can put inside this finite state control. And then you can actually start describing other Turing machines as little pieces of data and ask this machine to compute to figure out what would this machine do on this other thing. Turing machines became our symbolism for what is an algorithm, but it was also our architecture for how would you build a computer. In fact, it directly led to the von Neumann architecture. Von Neumann simply changed this thing to call it a CPU, and he called this thing, he built a matrix out of it and called it a RAM. But other than that, really, the architecture did not change. And one of the central themes in the von Neumann architecture is this notion of a stored program computer, which is really a different phrase for a universal machine. It's just the same thing. It's one machine, which once you build, the rest of it can all be just fed in as data. You can program this machine to do anything else. And by the way, this is a remarkable thing that's true about computer science and no other field of engineering that I know. One machine that you build is sufficient to solve all the problems that you want to solve. May not be fast enough and big enough, but really the one architecture is sufficient and the one machine can be programmed arbitrarily. Only thing that's usually missing in practical machines is an infinite tape. The other side of the story starts with the theory of communication. So this is a theory that started in the 1940s. This is the advent of the digital age. Before this period, people probably sent information around in the form of music and spoken voice. And those things were very robust to noise. So you hear some garbled somewhere and you can still figure out what was probably said, or you ask people to repeat the thing. We were not doing it at scale and we were not doing it with digital information. Digital information tends to be very, very, very unstable on its own. So for example, English is unstable. We said we are not ready. Bob heard we are ready because there's a noisy channel of communication between Alice and Bob, and does completely the wrong actions as a result. So communication media are always noisy. It was true in the 40s, it was true in the 50s, it is true today, and it'll be true 100 years, 1,000 years, 10,000 years from now. As long as humanity is alive, we will actually have to face the consequences of this. The nice thing is we know how to deal with it. Why do we know how to deal with it? Because of the seminal work of Shannon, who just put in these little two boxes in the communication channel. Before Alice sends the message, puts the message out on the channel, she encodes it. Before Bob actually tries to figure out what Alice was sending, he decodes whatever he gets out of the channel. Encoder and decoder in Shannon's architecture were just arbitrary functions. You usually work with k, which is much, much smaller than n, maybe 0.9n, maybe square root of n, or maybe 1/2 of n. All of these are okay, but k is much smaller than n. And you expand the message before you send in, because so you put in extra redundant bits saying, oh, these k bits are what I want to send you, but also here is some extra information about those k bits, just to make sure if one of those gets corrupted or one of the later bits gets corrupted, you can figure things out. And the decoder tries to invert the process and says, oh, we know that there's some possibility of error, but let's figure out what message it could have been that Alice was trying to send. So you expand here, and then this is decompression. So ideally, you'd like decoder to be the inverse of the encoder, but also even if you have errors, it'll still preserve the reception. So this architecture is already amazing. Why? I'll get to it in a moment, but Shannon was putting in encoders and decoders. This is after Turing's work, but before von Neumann's work. We had no idea how to build these encoders and decoders in those days. 1948, there were no computers sitting around. And Shannon just said, well, let's assume we can actually compute these functions and let's see what would happen. He got some amazing theories, amazing results. I'll tell you a little bit more about those in a moment. But this, tension between computing and communication is really, really, really interesting. It's on the one hand, we see that these are very interdependent technologies. How are you going to build an effective communication channel? You will have to build an encoder and a decoder. Okay, these are computers. So let's go back a page and see how we built computers. Well, we have to build this finite state control and this infinite memory. That's storage of information, which needs to be reliable. These two need to talk to each other, which needs to be reliable. All of this is reliable communication. So to build this, I have to put in two computers here. To build this, I have to build further computers there. Everything seems to depend on the existence of computers. Computers are needed to build communication channels. Communication channels are needed to build computers. So there's a cyclic twist, which is quite remarkable. So these are definitely interdependent as technologies. And yet, when you look at the famous companies, the famous products, Bell Labs, IBM, and everything that happened in the early days of communication and computing, they were very well separated. They really kind of abstracted each other and worked off of them. These abstractions developed a lot built in this thing, but it somehow managed to work. And on the theory level, also, it is really the case that the Turing theory and the Shannon theory barely spoke to each other. There was a brick wall separating the two. It's not the same brick wall as we will talk about later in the talk, but there's a brick wall that was really laid between the two. It was very good for each one of the theories. When we wanted to say what could be done with computers, we almost rarely tried to say, oh, but at the end, there's these bits which are noisy. And when the Shannon theory of communication got developed, we rarely ask the question, oh, how easy or hard is this function to compute? What's the limits of computation? Very little of that was crucial. Yet the theories, are intertwined at the very basic level. And this is and today's talk is sort of sitting in this intersection. So to understand where this problems in the intersection, or this class of problems in the intersection, comes from, I'm going to talk about some very basic stuff. So let's recall what Shannon's theory actually proved. He said, well, we don't want to use a communication channel wastefully. What does that mean? Alice wants to send a k-bit message. She encodes it. If it becomes a very long message in comparison to Alice's message, that's a lot of channel usage. So if you start with k bits here, and this is n bits here, you would like k over n to be as large as possible. On the other hand, we also want this message to be decodable. Even if you have errors, after you've encoded the message and then the channel has made its errors, when the decoder acts on it, we want Bob to be able to recover the original message, not an approximation to the original message, exactly what these messages were. So what are the best encoders and decoders with the highest rate? This is the kind of question that Shannon asked. And one of the nicest things about the Shannon abstraction is he sort of set aside this question. By the way, I see that people are saying, yes, electrical engineers thought about it. Yes, true, they did. But at the same time, I would say things that I read in Berlecamp's book on 25 years of coding theory and so on, very clearly tell you how much they appreciated algorithms and how much they did not appreciate algorithms. So I would say there's a debate there, but why not? But it's not as clean as we think. Existence of an algorithm is not sufficient, and there are some brilliant algorithms that were developed in this area by electrical engineers and by coding theorists. All right, so what's the best encoders and decoders? Shannon's theorem told us what were the limits that were possible. This ratio k over n, he said, could be pushed as much as entropy 1 minus entropy of p, provided our bits are being flipped. What the channels transmits bits, and these bits are flipped with probability p, And then you get some formula saying this is what you can achieve. I don't want to elaborate on what this formula is, but I just want to tell you about two extreme cases. If the probability that a bit is flipped is 0, this formula says that you can transmit at rate 1. And this should not be very surprising. If no bits are flipped, there's no need to do any encoding. There's no need to do it in decoding. You want to send a k-bit message, you send that k-bit message. And Alice sends that message, Bob receives it. It's that 100% rate. On the other hand, if p is a half, meaning every bit is flipped with probability half. I send this 1, you get a 0 with probability half, a 1 with probability half. I send a 0, you get a 1 with probability half, and a 0 with probability half. It doesn't matter what I send. What you're getting is completely uncorrelated with what I'm sending you. There is no capacity to convey information in this channel, and so the rate should be 0, and that's what this proves. But even more interesting, this rate is monotone decreasing for p in this range. So even if you have 0.49999 probability of an error, this is saying there is positive rate in the channel, and just by expanding the message by a constant factor, a large constant factor if that's your p, but still a constant factor, you will be able to achieve reliable communication. And this is something that's meaningful. People currently are able to do things like the following. You start with your amateur radio aficionados. They sit, say, in Japan. They send some signal out into the cosmos, and there are comet trails out there, and these comet trails reflect some of that signal back to, say, New York. That's a pretty long path for a message to take, with a lot of unintentional communication. The probability that a bit that you send would be recovered correctly by this process is 0.4999. And indeed, they can actually use this channel to communicate effectively. It's a game. That's not the best way to communicate from Japan to New York today, but it's doable. So, and this is explained by this theory and this formula. Okay, so it's a really remarkable theory, exceptionally successful. So what were the challenges after Shannon's 48 work? I mean, he's already pinned down exactly what is the rate you can achieve. Shannon's theory was very non-constructive, or at least the theorems were built on very non-constructive elements. He picked the encoding at random. The decoding was just brute force decoding, look at all the possible messages and find one which was most likely. And this leads to very, very slow algorithms. Encoding takes 2 to the k time, and decoding takes 2 to the k time, finding it, and encoding can even ask for just to search over a space of size 2 to the 2 to the k. So the algorithmic challenges since 1948 have been, can we find some ways of encoding and some ways of decoding which are more explicit? They should take polynomial time. Okay, so this, I would say, is where we start the second phase of the talk. So we are going to use this as an excuse to talk about one class of explicit error correcting codes. These are
Madhu, there's one question.
Sure. One second. Let me just finish the sentence.
I think you addressed it, but I mostly want to just raise it so that the audience also doesn't feel shy of raising other questions. So it's a question I asked, and I think you addressed it, but let me just. Isn't noise something that also affects computation and not just communication? Shouldn't there be a similar theory for correcting, like you have a NAND gate and then it doesn't quite do what it's supposed to do? So why are these two such different things?
They're not very different things. That's a great point, Ellie. So there were a few pieces of work in the 70s due to Pinsker, and I forget some of the names over here. And then in the 80s, Pippinger is another name that's floated there. Gall and Anna Gall and Peter Gach have works in this, who talked about what happens when circuits are noisy. And you can abstract a noisy circuit as saying it consists of a lot of little elements which are communicating with each other, and these communications are leading to noise. And in these kinds of cases, you don't have the luxury of putting a universal computer and the most effective encoder and decoder to decode. You have to do something a lot more rudimentary so that it can be built in at that scale. So one of the amazing things about computing and communication is each depends significantly on the other. And the fact that we were able to escape this seemingly cyclical reliance of the two on each other And build computers was a miracle then. And if we can achieve the same miracle in the setting of quantum, we would have quantum computers today. The biggest challenge in quantum computing, at least in universal quantum computing, is our ability to build an error correcting code which can be stabilized by a quantum algorithm and a quantum computer to be stable enough so that we can maintain it for, let's say, a second. Once we're over that hurdle, we'll suddenly be able to compute everything. But up to that point is where the challenge is.
Madhu, there's another good question by Amit Agarwal. I'll read it. Can you provide some high-level intuition as to how Shannon proved that encoding and decoding can be done without giving an explicit construction?
That's a beautiful thing. I mean, it's a remarkable result. In 48, Shannon already published this work. He picked the encoding function at random, which meant he said that if you pick a random function, then with very high probability, this a decoding algorithm constructed specially for that function would work. This analysis, once you sort of set it up in the framework of math, is not hard at all. It's really, once you've seen a little bit of the law of large numbers in action, you can actually go through the machinery and prove the things that you want. But it's very subtle reasoning and thinking to say, I'm going to pick the function at random. And in fact, the way Shannon thought about it, he said, let's assume that after the message to be communicated has been determined and the channel is already acting on it, we pick the encoding function now. So somehow much later, as opposed to the way we would do it, which is we'll pick the encoding function today, build a machine to communicate, a system to communicate, and then use it. He inverted everything. And this inversion is very useful in the analysis. Okay, great question. So shall we move on, Eli?
Yes, thanks, yes.
Okay, sounds great. So today, I'll talk about one family of codes. I hope people are somewhat happy to see algebra. You don't have to be the most comfortable with it, but at least you should not have an inherent fear of it. And once you have this little bit of happiness with algebra, these are about the most simple families of error correcting codes that I could describe. And they work like a miracle. I mean, they are really amazing. So for this part of the exercise, so imagine I'm sending you not bits of information, but bytes, okay? So I want to send you, let's say, 4 bytes of information. The first byte, each byte I'll view as a number between 1 and 128. So that's the, I think, oh, maybe it should be 256, but whatever. Yeah, I mean, even if it was. So yeah, so some number between 0 and whatever 2 to the 8 is. And these bytes, we view as some numbers, and we say, okay, I want to send you 4 bytes, let's say 100, 23, 45, 76. And instead, I will be thinking of it as if I'm sending you an abstract object, a picture in space, which is this polynomial given by the same coefficients, 100 plus 23x plus 45x squared plus 76x cubed. Okay. The way I will send this polynomial, I have multiple ways of sending polynomials to you. I could send you the coefficients of a polynomial. Okay. That would have been not so useful. I mean, I had message in this form. I'm sending it to you back in that same form. So that's not quite so interesting. Instead, what I'll do is I'll evaluate this polynomial on a bunch of points, p at 1, p at 2, p at 3, p at 4. I keep going on till you get impatient with me and you ask me to stop. Okay, so n places, whatever n is. Okay, and why is this interesting? Why is this useful? Well, we know that the first 4 values already suffice for you to know the coefficient. This is called polynomial interpolation. And it tells us that if I tell you the value of a polynomial at 4 places, then I should be able to figure out the coefficients of the polynomial from it. But it's not necessarily the first 4 places. I could also tell you the value of the polynomial at these 4 places, maybe p of 1, p of 3, p of 4, p of n. I should tell you that this is the value at 1, that is the value at 3, this is the value at 4, and that is the value at n. But if I do, that's also good enough. So you can see that there's redundancy in this information. I could go around erasing some of these coordinates, but as long as you know what's been erased and what's been preserved, 4 pieces of information suffice, any 4 out of these n. That's some robustness, but it's even better. It turns out, and that sort of is what is stated here, if you want, you can handle n minus k erasures when symbols have been erased with a placeholder saying this is where something has been erased. You don't see what it is, but it's not like we squished everything back into four bytes. And it turns out it's also going to be capable of handling n minus k over 2 errors. And the reasoning for this is very simple. If I have some message that I sent, and it turned out that after some corruption, I got this. So maybe these things got corrupted, and I got that. And some other thing also agrees within in the same places. You could ask, how often did these two agree? These are both evaluations of polynomials. They cannot agree in too many places. And if two polynomials cannot agree in too many places, then half of that many errors is also sufficient for correction. So this is one of those cases where we have an explicit encoder. We can, and by the way, if you're worried, oh, don't these numbers start exploding very soon? Maybe P of n is like, if n is 100, then P of n may be like, not a number between 0 and 256, but 10,000 or 100,000. Well, we can always work modulo some prime or in some finite field. And for those of you who know what that means, to keep these evaluations small, bite-sized. So none of these is going to be large, and we are going to be good enough. And now comes the question, okay, this is great. If I have this information with a few errors, I can still, in principle, recover the original polynomial, but is there an efficient algorithm? And Peterson in 1960 gave this remarkable algorithm. Peterson is a coding theorist, legitimate, and this is a remarkable algorithm. So yes, there are existentially very, very amazing algorithms in the field. And I even think that he had to actually justify why did he work hard to find this algorithm as opposed to brute force search. And he gave a justification, says, oh, this is an algorithm which runs in polynomial time, whereas the other things run in exponential time. So it's a very early example of somebody recognizing the difference between polynomial time algorithms and exponential time algorithms. A very, very non-trivial algorithm, something that if you asked as a homework problem in your first algorithms course, you can be pretty sure nobody's going to solve it. So nobody's going to discover this algorithm by accident. It takes a lot of thinking, and we'll try to give you some idea of how you can do this recovery in the next few minutes. Okay, so this is how we could work. In fact, in what will happen in the rest of the talk, I'll actually even give you an algorithm for a more complicated problem called list decoding. What's list decoding trying to get? So let's imagine I wanted to send you one possible message, P1, and that was some n values, n bytes. If I want to send you P2, maybe that's some other n bytes. But what you might receive might be either, the first half is like P1 and the second half is like P2. Okay. This proves to you that 50% errors cannot be dealt with, right? Because if I received this sequence, did I come from here or did I come from here? Each one of these is a message that explains the data on 50% of the points. So 50% errors is impossible to recover from. This was our thinking initially. But it turns out that there is this notion which says, well, okay, I mean, imagine you have this old DVD that was recorded, has all the family photographs from 20 years ago, and it's totally scratched up and so on. And there are two possible solutions. You go to store one and they say, well, this is over the 50% limit. No, I can't do anything to help you. The other store goes to, you go there and they say, well, here are two different DVDs which we can hand you back. Either this was the original one or this was the original one. Maybe this helps you. Of course it helps me. One of these is the prized family photographs. This may be pictures of Martians. I want this. I'm happy with this list decoding solution. This list decoding is what we will aim for now. And it turns out that list decoding is something that not only can be done effectively, but it's also really fun to do effectively. In fact, I'll give you some examples of instance of the list decoding problem and see how we'll solve it. So what is this problem? The problem that we have is the following. We are given a bunch of, what happened? There was some polynomial p that I transmitted. We agreed that I'll send you p of x1, p of x2, p of x3, and so on up to p of xn. I mean, if you want, you can just say xi is I. Okay. And what you received was y1, y2, y3, and so on up to yn. Usually yi equals p of xi. But there are errors. So not always, or noticeably often this is happening. What we'd like to do is find p. That problem has a very simple description. You get these parameters, the degree of the polynomial, how often do I expect to see p of xi equal to yi, and how many places I've evaluated it. And they translate to n points in the plane, x1, y1, x2, y2, and so on to xn, yn. Our goal is to find a polynomial which has the right degree and has the right number of agreements. Okay. And let me give you an illustration of what this problem looks like. Here it is. Here we have 14 points in the plane. And I'm looking for k equal to 1. K equal to 1 is nice because we can eyeball it. K equal to 1 means I'm looking for lines, degree 1 polynomials. And lines are easy to find. We can look at the solution, and I want lines which pass through at least 5 points. Okay. So hopefully people understand from this picture why list decoding is necessary. I can see one line, which is this one. I can see another line, which is that one. So no matter what, if you try to answer this, your answer should include both of these. But are these all? Is there one more that goes through 5 points? I want you to think about it. And let me say that no, there is no more that goes through 5 points. Let me even give you a proof. This picture is a proof that there are no lines which go through 5 points. What have I drawn in this picture? I have drawn a curve, algebraic curve, something that can be written in the form some function of x and y is 0, and that function is some polynomial in x and y. And every point is a 0 of, is on this curve, is a 0 of this polynomial. Okay. And if you just stare at this curve, we found the solution. If there was any other straight line which passed through 5 points, it would look like something like that. It would either have to touch this line twice, or that line twice, or this circle 3 times. And none of those is possible. So this is the essence of our algorithm, and it leads to a polynomial time algorithm, and some of the details of that are mentioned in the slide, but you can ignore it. Okay. So it's not only is this algebraic problem solvable, it's actually solvable by fairly simple ideas, and ideas that are actually quite useful. So here is another example. This is with correcting even more errors. So we have 11 points in the space now, xi, yi. I'm looking still for degree 1 because I want us to be able to eyeball. And I want to find lines which pass through at least 4 points. So if I'm right, this is a line which goes through 4 points. That's another line which goes through 4 points. Here is another one. And there may be more. By now, I can't see the points from my lines, so I'll stop trying to find more. Okay. But there are probably more. How do we know which ones are there? How do we know when to stop? Okay. And can we find this in time polynomial in n and k? We're doing this all for k equal to 1, but we'd really like to do this for large values of k. At the end, I'm going to be k is the size of the message that I'm sending, and we want to think of k as almost n, 90% of n, 80% of n. Okay. So turns out you can do this, but what you would like to do, what you need to do to get that is, whoops, okay. what we will do is find a polynomial in two variables, x and y, of degree at most 7, which passes through every point twice. Why twice? Because we were seeing this many points where these lines were passing through them twice, and we want our final solution to include all the lines. So you really need to have you might as well require, you're not going to get coincidentally a curve which passes through all the points also happens to pass through all the points twice. So we'll actually insist on it. You can insist on it algorithmically. And what makes all of this easy? There are two important lessons. You're always looking for solutions that explain all points. You never ask for solutions which go through most of the points, always all. And that makes it a much easier problem, just linear algebra at this stage. And the other thing that's working in our favor is we had a univariate problem to solve. Find me a polynomial in X which goes through many points. We converted it to a multivariate polynomial in two variables, X and Y. Why did it help? You suddenly have many more parameters for any given degree. If I want to find a polynomial which fits n of these points, in one variable, I would probably use degree n. In two variables, I can use degree something like square root of n. And that difference makes all the difference here. And once you put it together, you get an algorithm and it corrects lots of errors. And I will not dwell on the details. The picture is sort of the proof. This picture, by the way, is also a proof that there is no other line which passes through these points. I mean, these two blue lines you should ignore. Those are just spurious. But if you found me one more line which passes through 8 of these points, through 4 of these points, that line and these points would have this curve that we've drawn, this product of things, would have 8 points of intersection counted right. And you cannot, but there are only 7 lines here that I've drawn, including the blue ones. So you cannot have 8 points of intersection between, so if I drew a new line which would pass through this collection of points, say this one, the number of intersections is at most the number of lines that I had originally, and there were only 7 lines in this page. So I cannot get these 8 lines, and that's why that's a proof that you don't have any more lines that explain that go through 4 of these points.
Okay. Madhu?
Yes.
There's a couple of questions.
Great.
Okay. Good. This is a very good place to. Okay. So the first question by I believe Amit Agarwal asks, vague question: is it possible to fruitfully see RS encoding decoding through the lens of Fourier transforms? After all, Fourier transform is essentially polynomial evaluation, though not necessarily over finite fields.
Great. Great question, Amit. So my answer to this is to go in the opposite direction. Historically, what happened, and this is, might be amusing to some and annoying to others. Historically, what happened was people realized this connection between Fourier transforms and polynomial evaluations and used this very effectively. They made the encoding very fast. They changed what the code even looked like. Instead of evaluations of polynomials, they got these were coefficients of some new polynomials and so on. And what happened over the course of history, Peterson's original algorithm actually works in the Fourier domain. But the first step in his algorithm is a Fourier transform, and then there are other things. And this got preserved for many incarnations. And I think personally, these prevented us from understanding what was really going on, because we were doing a Fourier transform once before we even set up the problem, and then a Fourier transform afterwards, after the problem was set up. The two of them together were computing the identity function, but nobody noticed this, and this really led to confusion. To me, I think this is the correct proof. There is no mystery about polynomial interpolation. There's only some simple linear algebra, no Fourier analysis needed. And the Fourier analysis is is maybe useful to extend this kind of thinking to other scenarios. But for polynomial evaluation, actually just the simple algebraic geometry that we see here is the essence of it.
Okay, the other question. So first of all, I apologize. I misread from the chat. Both the previous question and this one actually come from Madhu Shiragji. So the second question is there a good intuitive explanation of why requiring multiplicities helps correct more errors other than just reading the proof? I mean, I guess the proof that it works. Yeah.
Good question, Madhu. The answer will probably make sense only to you and a few others, but I think the answer is hidden here. There are settings where we can create lots of lines which pass through very few points, and these settings will typically involve every point passing through 2 or 3 or many lines. If you want to recover the explanation which has every point going through many lines, it's not going to happen by coincidence. You have to require it, and requiring it suffices. The fact that it suffices is a calculation, is a little bit of a, the proof tells you that. But the fact that we should have been thinking of this in retrospect is seems very natural to me.
Okay, thanks. Yeah.
Okay. All right, great. So I have about 15 minutes left, and in these 15 minutes, I want to go a step beyond. And now I want to sort of lift a level higher. What are error correcting codes doing for us, and what else can they do for us? So, the way I think of it, data is just zillions and zillions and zillions of bits, each one of which could be doing things on its own. So it's like this pile of sand. Any one of these sand particles could, reside in any one of many positions, and they could be very independent. There's no structure to this thing, nothing which sort of says if this particle is here, then the other ones have to be forced to be here and there and there and so on. Anything could happen. And when data sits like this, errors are unmanageable because any one of these bits could have been an error. Raw data is like this. Encoded data, after you put the data through an error correcting code, looks like a brick wall here. And this is a new brick wall, and this is going to be the metaphor from going forward. It's a glue that binds all these pieces of sand together and creates something which is very structured, and you can't really move pieces independently. The moment you do it, well, it's not like one piece would lead to a collapse of the brick wall, but they are all, each one is holding it in place. They are in a given position. As you start moving enough of them out of the thing, the wall will collapse in integrity, and then it'll collapse. But each piece of sand is now sort of somehow constrained. And that's what an error correcting code does to data. So this is what allows us to use zillions and zillions of bits of data and think of this as, oh, this is one unit of something. I generated this data while I was doing this particular test of that hypothesis in space, or this hypothesis on drug design, or this hypothesis in biology. And I think of that entire piece as one integral unit. I do not think of it as a zillion collection of bits, which I might have to independently explore every time I look at it. Wouldn't it be great if other things that I did with this data can also be preserved? So, I mean, why do we generate all this data? Well, one answer might be, well, I generated a huge amount of data to, in fact, generate even more huge amounts of hypotheses. If you live in that world, good luck to you. I don't know what we're going to do with all these hypotheses now. I think what we try to do is a few hypotheses, 1 to 100 hypotheses that we are interested in testing. We generate a lot of data. We produce these things. Now that I've seen that one of these hypotheses is confirmed by this data, could I write that down in a piece of stone, make sure that everybody can trust it? So are we living in a universe like this when it comes back? Or do I have to go back and look at each piece of data again and say, oh, yeah, everything looks okay? Or can I just look at this and say, okay, I'll tap this wall a couple of times and say, oh, yeah, this looks good. This turns out to be the universe we live in. This is the universe that's the core, I think, of Starks and Starkware and companies like that. And this is what is desirable, this is achievable, and this is what I want to talk about in the rest of the talk. So in fact, I'll go a step beyond. So we want to, we start with zillions of bits of data, we build some structured elements out of it, and then these structured elements, we put them together into something that is useful. And it is this property that we want to test. A building inspector comes in and says, is this building going to be livable for and usable for the purpose that you are envisioning? 2 families or 1 family with a kid and an elderly resident, etc. Will this thing work? Can we check this with roughly the same kinds of complexity that it takes to describe this property, okay, or even less? So given in the data information theoretic mathematical sense, what this translates to is the following. I have some k bits of data that I generated. I analyzed it and figured out that P of X is true. So some property about this data is true. Can we store this as some larger piece, which actually sort of emphasizes, clearly tells you that P of X is really 1, okay? I don't have to read all of these zillions of bits of data again. I definitely don't have to do all this analysis again. I just immediately know that P of X is 1. Can we have this property? Okay. So it turns out that this question can be formalized. This is what leads to the idea called probabilistically checkable proofs, or PCPs. And the PCP theorems tell us, and this relates to the 3 in the talk, in the title of the talk, that we can do this with a tiny overhead in this size. I mean, if I had originally some number of bits of data, I might have to expand it, add some new pieces of cement and other such things before I can get to the structure that I want, but it will actually be testable very, very effectively. And what will we be able to convince is this verifier will look at this, encoded structure. So we started off with these bits of sand, we built this house, the inspector will look at it in a very few places and conclude that this is meeting the standards that I wanted. P of X is true. This is really what I wanted, okay? And the PCP theorem that tells us that you can actually do this. And this, I think, is kind of remarkable. What's even more interesting to me is that this comes from the fact that, we can work with polynomials, and with multivariate polynomials, we get a lot of power, okay? So PCPs, when we want to build, how is this PCP theorem proved? I want to give a very high level bird's eye view of it. There's 2 ingredients to it. One, which I call simple structural tests. They just look at this piece of brick wall and say, is this, does it have integrity? Did you start with some pieces of sand and construct a wall according to the design specifications of how walls are supposed to be built? This is something that is a well-known element independent of how many, what kind of a building you want to build. Is a wall integral? It has nothing to do with the exact design of the building. It's just a structural test. A building inspector will come and knock on the wall a few times and say, oh yeah, this looks structurally solid, let me go to the next wall, etc., etc., and eventually say, yes, structurally the building looks solid. The thing that's very intriguing in the information theoretic setting is we don't have the information theoretic analog of a wall or a hammer that can knock on the wall. We really are just, at the end, we have zillions of bits. When we did the error correcting code, we created a mega zillions of bits, but it's still a collection of bits that can actually act independently. What does it mean to test it? Our verifier will look at one bit, will look at another bit, and so on. That's like saying, going into this brick wall, you don't get to hammer this with a hammer and test the overall structural integrity. You get to probe one of the sand items, molecules here, another molecule there, another one there, and then you have to conclude, oh yeah, this brick wall is good or bad. And the remarkable thing about working with information is this can actually be done, okay? So what happens in PCPs is there's really 2 different ingredients. One which says, going from any general statement P, we can actually prove that that statement P holds. Some of this uses the traditional theory of NP completeness, which says instead of looking at some property P and saying, oh, this is happening for this particular collection of bits and some other P for some other collection of bits, you can convert it into a uniform statement of the form. Here is a graph. Is this colorable with 3 colors? And proving that this property holds about the data is the same as proving this graph that you have is colorable with 3 colors. This is traditional NP completeness. And once you have this, it puts us in a frame of mind where we can use polynomials and remarkable things about polynomials to say, well, you know, once we have this ability to test if lots of pieces of data, something that looks like this is really a brick wall, I can build any property out of it with a constant number of brick walls. Some 4 brick walls suffice to prove any general thing. So I need to only look at sort of structures involving 4 walls. So somehow this combination is what allows us to build PCPs. I was very ambitious, and I even sort of wrote down the reduction which tells us why 4 brick walls suffice. The details are not important except to those of you who want to follow this, and this talk will be posted online and you can sort of look at the intricacies, but this is the full reduction. And if you can prove that there exists A, B, C, D such that this resulting polynomial is identically 0, then that implies that some graph that we are starting with is 3 colorable, which in turn implies that some data satisfies the property P. Okay, so it's here, it's a subliminal channel, you can explore it later, but right now I will not talk about it. Okay, so that's how PCPs are built. And I just do want to say a little bit about how PCPs emerged historically. The very original motivations was really to try to understand some cryptographic interactions, and this happened in the mid to late 80s, where we said, well, if we could build these kinds of things, I mean, these PCP-like objects are really telling us how this cryptographic interaction is connected to the security of this other cryptographic interaction. We really didn't think about PCPs as much more than a technical tool at that stage. In the 90s, we suddenly changed and we said, oh, actually, you know, PCPs are miraculous because they allow us to say that something is not doable. The fact that I can build PCPs says traveling salesman problem is not only solvable efficiently in polynomial time, you cannot even find a 0.01% approximation to TSP efficiently. You cannot color 3 colorable graphs with 5 colors efficiently, etc., etc. Lots of interesting statements can be proved because PCPs exist. Both of these are not quite the same as the motivation that I spoke about, but this has suddenly re-emerged in recent years. PCPs are interesting because they allow us to encode and display data in a form where some aspects of the data, some properties that are held by the data are immediately checkable. There is, what kind of things, I mean, like you have this long commitment to a new commitment to a blockchain. You want to know that this commitment is indeed passing the test. You could do the entire test on your own, but PCPs tell you that you can actually have verifiers that really just sample some of these things and work with them. In order to get to this point, we had to do a lot of work. I didn't work on this part at all, but Ellie and his collaborators and others in the community have worked very intensely on these questions. These things actually involve novel structural tests. How do I prove that some data has been encoded properly? How do I prove that the encoded data actually satisfies the expectations of the specific test that we are designing, say in the blockchain setting, say in some other setting? There's also, by the way, novel models of that go into this, but I won't even talk. So it's not, we usually don't work with core PCPs, but interactive PCPs, but I won't talk about it. So one remarkable thing that actually happens in this entire story is, for instance, in one of these works, and there may be other works in this regime, when you want to prove that some large piece of data is really the encoding of some degree k polynomial, you can, these theories say that, oh, you can somehow reduce it to proving that some smaller piece of data is a polynomial of degree k over 2. And this ability to squish the things allows us pretty soon to apply logarithmically many steps and come down to some concrete things. So you look at this f in a few places and this g plus alpha h in one place, and then maybe something else in one more place, etc. And soon you're down to some simple statement. The analysis of this turns out to use exactly the same list decoding and the same principles and so on, polynomials, low degree polynomials with errors, how do you fix them? And so it's quite amazing that we've sort of circled back to this thing saying, oh, all these complicated objects, but at the end, essence of it, we really need to know how can you deal with math and the thing. So conclusions, I mean, in this arena of how can you protect data and how can you verify its properties, there are some miracles that seem to be possible. And in many of these cases, I mean, these proofs by pictures, I think, sort of should be very convincing that this algebra plays a huge role, and this algebra is not very sophisticated. It's really considered, very, very elementary, that manages to lead us to all these places. Thank you very much. I'll stop here and take questions. Ellie, you're muted.
So thank you, Madhu. We'll take the last set of questions. So please type in all your questions now. I tremendously enjoyed the talk. I'm going to go over the questions. I wanted to point out that just now, as I'm listening to this excellent talk tonight, I love this metaphor of data as sand, error correcting codes as a wall, and PCP theorem as inspecting a house. I think it's a beautiful analogy. I already tweeted it. Going to Mahdi's question on Fourier transform, as being something used in the decoding algorithms, as you were showing the last slide, I realized that perhaps in decoding today, the more modern algorithms are not, don't use FFTs, but for reasons, we don't completely understand, a lot of the efficient PCPs and interactive PCPs and things like that happen to also use FFTs. And then also, and of course, they also need all of the non-FFT decoding. So there's I just realized this, but I don't know. So I don't know. Do you have thoughts on this, or?
Yeah, that's a good one. So I stand corrected both by you and Madhu. I think the FFT analogy is very important, but I think it should come as a second thought. The first thought should be, let's just look at the simple linear algebra question. How can we solve it? Then when you ask about efficiency, the fact that the Fourier transform can be conducted fast, hence the FFT, is something that's very effective, not only in making sure that our algorithms run fast, but as you point out in some of these Stark-related works, it makes the proofs very small. The proofs become succinct because it's an FFT that you're trying to, whose transcript you're trying to encode.
Okay. Thanks. So, by the way, I didn't mean at all to correct you. I agree with what you're saying on error correcting. I just realized that other aspects do happen to use. Okay, so I'm going to read the questions, and so all the listeners who want to, they're terrific questions here, and if you have any other questions, please type them in. Okay, so the first one by Bengt says, Madhu made a point of computation and communication depending on each other. Yet my computer doesn't use ECC memory. Wireless and other digital communication hardware assumes decoders and encoders work perfectly. So it seems to me that computation and communication are still largely considered separately. You mentioned quantum computers, but that seems pretty exotic. Do you have other examples of when we must consider computation and communication together? Any non-blockchain examples?
So good. So if you really, I mean, there are various ways of interpreting the question. One could say, up to a certain level, I actually just build a piece of hardware and I assume it's not going to be error prone, and then build an error correcting code and decoding on top of it after I built a pretty large module. And that's how our current computing goes. It's true. I think that if you consider an email that I sent to you today, and you ask how many layers of error correction are going on and how many layers of error decoding is going on, you will find many, many, many steps. I mean, there is an outer level in software, and as you go down the layers of communication, the communication protocols, different types of error correction methods are imposed at each stage, including at the point where I type something into my keyboard and it's sending information to my computer wirelessly. There will be some error correction going on, maybe as simple as a parity check. Okay, so it's because of this thing that for very simple short messages, we can't afford to have a lot of computing going on to the decoding. We put in very simple error correction code, sometimes as simple as repeat the message twice, thrice, take the majority vote. If I'm the fact that in a piece of compact disk, I leave so much space between two different bits that I put on this compact disk or this storage device is related to the fact that if I made it any smaller, that would be, I would get interference from one from the other. But you could think of this extension. I could think of this large piece, say, let me draw it. This large piece is really a collection of tiny little pieces which I just happen to repeat information. So there's a repetition code that's acting even there. So a lot of this question, I think, is there's different kinds of error correction codes, different kinds of error correction mechanisms. Sometimes we just have to work with our hands to make sure that the computation is so simple that any error correction that it needs to do is also folded in, and we can talk about the resulting effects. And people do talk about the work on noisy circuits, I would say, is a very concrete example. If you want a particular reference, let me just, I mean, this is not the only paper in this area, but Gal and Gach have a paper on noisy circuits and how to use error correcting codes there. This goes to the essence of the question. When you have computing and communication built, sort of joined at the hip, how do you deal with problems over there? Yeah.
Okay, another question by Mustafa. Would you tell us recent research directions in the interplay of algorithms and information, and how both fields are benefiting from each other?
Great. Yeah. So I think I look at, so in both directions, people who are trying to build devices that are communicating and trying to make this more and more effective. One of the remarkable classes of works in the last 20 years is this discovery of something called polar codes. This sits at the core of information and communication and computation. The essence of this theorem is saying, of this construction says, here is some class of error correcting codes that we can build, or encoding and decoding algorithms that we can build, whose claim to fame is that they can be achieving Shannon capacity effectively computationally. So if it were not for the algorithmic result, we would not be particularly interested, but it has a remarkably fast algorithm associated with this thing. So we are trying to correct more errors, and we are trying to deal with more weaker channels. And this has been, and whenever we want to do this, we have to do this effectively with efficient algorithms. We cannot afford to have inefficient algorithms. And this remains a challenge. Every year there are new decoders that are sold in the form of DVD players or whatever is the newest form of a cloud recording device. A very fruitful area of interaction between the two fields has been the area of local correction. You could ask the question, if I have some information and I've lost some piece of it, I have this information posted in a cloud server, but one of the servers went down. Can I now quickly, but I need to do my tweeting now, not 10 minutes from now. Can I recover that information quickly? And people have found effective ways of recovering that information by looking at a couple of other servers and quickly rebuilding this the server that has collapsed, while at the same time making sure that if you have multiple servers collapsing, well, that must have been a catastrophe. Why would two servers go down at the same time? Well, in that case, we won't recover the information in 10 minutes, but over the course of a day, we will be able to recover it. How are these achievable? These are achieved by these codes called locally repairable codes or locally reconstructible codes. And these actually went back to ideas that started like PCPs. PCPs have local error correction and error detection built into it in a very different environment. By the time we ported it to we as in the broader community, electrical engineering and computer scientists included, by the time we ported it to this thing, it took many years, and we simplified the problem to the point where solution could be efficient and effective enough to be used.
Next question. Is there any connection between error correction and computational geometry? This time it is by Amit Agarwal.
Mm-hmm. Error correction and computational geometry. I haven't. The specific, I mean, the only way I could imagine a connection between the two would be that we use the same kinds of insights, or we use geometric insights to solve this polynomial reconstruction question, which looks like a geometric question, a computational geometric question. So far, the two fields have not come together in some essential way. One of the challenges here is that even though these pictures that I drew and said, oh, look, can you find a polynomial which passes through a given set of points? In real, if you had really been thinking of computational geometry, I would have been looking at approximations. Every point might have moved by an epsilon, and I won't be able to detect it with my eyes. The solutions that we provide are not going to be so oblivious to the slight movement. They're very sensitive. So we can only carry these solutions out in finite fields, and then once you go to finite fields, many of the geometric insights go away.
So I'll ask the last question. I wrote it here. How did you get into this research, and are you surprised by how it turned out for you and for the field?
Okay, so was this a planted question? Did I ask you to ask this?
So no, I confess it was my own, but I think
I would say, I mean, many people have, when they're asked, how did you decide to do X? They have these, profound answers. When I was growing up, I saw this thing. To me, it has always been the path of least resistance. I think of research as somehow we are in some, universe. It's a graph, and we are doing a random walk on a graph. Each point represents some state of knowledge or some piece of information. And we keep exploring to see, maybe I'll find a path to something interesting. Some people look at this whole graph globally and I say, oh, here is this vertex that I want to get to. That is the piece of information that I target. I have usually always drifted around. I encountered polynomials accidentally. And in fact, so much so that when I was asked to defend, pass my qualifying exams at Berkeley as a graduate student, they asked me to present some research that I'd done. I picked research 1, nothing to do with polynomials. And the committee said, even though you have a published paper on this thing, we don't think you're going to work on this. Then I've said, oh, here's research area 2. And the committee said, I don't think you're going to make progress on this question. And they were right, because nobody has made progress on this question to this date. And finally, I pulled out of my pocket a third piece of research. And I said, this is something that I'm never going to work on again. And that was polynomials. And here I am today.
Okay. Professor Madhu Sudan, thank you so much for this very inspiring and excellent talk. I personally learned a lot and gave me a lot of good insights. Thanks to the terrific audience for the great questions and the chats, and see you next time.
Thank you all. Okay, bye.